Hey guys, Sebastian here, another video. This time I'm going over verifiable random functions and what they are. So if you're interested in these kinds of videos, please subscribe to my channel on YouTube, follow me on Twitter, and all this kind of good stuff. Okay, so what are VRFs? They're a cryptographic concept for how to generate seemingly random functions. And more specifically, this presentation will be based on a paper called Verifiable Random Function with Short Proofs and Keys by Dodis and Yampolsky. Okay, so what is a VFR more concretely, right? Well, a VFR is a pseudo-random function that gives a non-interactively verifiable proof of the correctness of its output. So what does that mean exactly? Well, by pseudo-random we mean that if I give you the input, 3, and then I give you the input 5, and I give you the input 7, and so on, the output always seems random. It doesn't seem like there's any pattern that comes out, right? And that's kind of loosely what we mean by pseudo-random function. Okay, and we want to have verifiable proof of the correctness. This is to say, even though it looks random, I can prove to you as the person doing the calculation that I did not just give you a random number. I actually did run this function, and this is the actual function output, and I can prove it to you. And when we say non-interactive, we mean not only can I prove it to you, I can prove it to you without having to give you any help, right? I can give, if you give me an input, say x equals 5, I'll give you the output and then proof of correctness, and then you can go in a dark room and take out your pen and paper and convince yourself that I did the right thing. Okay, so slightly more formally, we'll say if you have a private key pk and a secret key sk, the given input value x, you can compute y equals f of x, and then you will also have a proof of correctness pi of x. Okay, and we want this proof pi of x, that convinces every person that wants to verify that the result is correct, that y equals f of x is correct with respect to the public key and the verifiable random function. Okay, and so what is our goal? Our goal is to create a verifiable random function such that proofs and keys are small and a constant size with respect to message size of the input. And we'll motivate why we care about this in the future with respect to blockchain, and why we want these verifiable random functions, for example, in blockchain scenarios. And in this case, for example, the proof size is important because the smaller the proof, the smaller the blockchain, right? Alright, so let's go more formally another layer down into what is a verifiable random function, right? Well, a verifiable VRF is actually a combination of these three functions up here. This is say, okay, we have a function called generate, which takes k as an input and gives you a k-bit number, one of which is a private key, and the other one which is a one of which is public key, and the other one which is a secret key. Okay, our second function called proof is a function on x, and given the input x, it'll give you the function result f of x along with the proof of correctness pi of x. Okay, and then we need a third function called verify, and it takes the input x and then the function result y along with the proof. It returns either true or false, whether or not this is the result of a VRF, or whether or not you just gave me a nonsensical answer, right? Because we want to be able to tell whether or not they really did run the VRF correctly. And we'll motivate this again with the blockchain scenario later on in this presentation. Okay, so there are three kind of properties we want. The first one is uniqueness. Let's say if you have a common element x, right? There doesn't exist any y and pi pair such that for the same input x you get two different outputs with two different proofs, right? And we need this property, otherwise you could cheat, because you could say, okay, I ran my VRF on x and got this y, and then tell somebody else, oh, I ran my VRF on x and got this other y, and then people would be confused. They would not know which one's the true output, right? That's why we need this uniqueness. We also need it to be provable. That's to say, if you run prove on x and you get these output y and pi, then running the verification on these outputs returns true. And lastly, we need pseudo-randomness. This is to say no values of the function can be distinguished from random. And this is even after seeing other function values together with their corresponding proof. So just because I showed you the result on x equals 3 and the result on x equals 7 and so on, it does not give you any hint about what it would be, for example, x equals 11. So in order to show you guys how this works, first we're going to go over some basic concepts. We'll kind of go over this fairly fast. So one of them is called modular multiplication, and it's to say, basically what it is imagine you have numbers that loop around, right? And we say we loop around that a specific number called the order, right? So if we have an order 7, then at number 7 we'll loop around back to 0, right? So 2 times 5 is equal to 10, and then because we loop back at 7, their final answer will be 3. And that's called modular multiplication. And then now we want a number g such that g to the power of 1, g to the power of 2, all the way up to g to the power of p, or where p is the order of our group. All these numbers represent all the numbers in the group, right? So every number appears exactly once within this string g to the 1 up to the g to the p. Okay, if you have such a scenario, then g is called a generator of a cyclic group, and so this is what the cyclic group is. You can also note that if the order is prime, then all generators other than 1 and p, all numbers other than 1 and p are generators. You can make a more general statement than this, but this is all we'll need for our presentation. Okay, and so next up we're going to introduce bilinear groups. Okay, and so what are bilinear groups? Well, a mapping is bilinear if it's linear with respect to each of its variables. What does that mean exactly? I mean, to get that first we need these two definitions. One of them is the multiplicative cyclic group G and G1 such that the order is prime. Okay, and we say G is a generator of the group capital G. Okay, and we say a bilinear map. In this case, we're going to call the function E has 2 inputs, where the 2 inputs are both elements of this group G, and the output is an element of this group G1. Okay, and note that I do not actually give you the definition of E. I never say, oh, this is given this input gives you this output. Actually, you can set this to a large variety of things. And actually, I have a link in the description of this video, which is a blog post written by Vitalik that shows how bilinear maps are used in, for example, elliptic curve cryptography, and how, for example, in this case, you could use elliptic curves in VRFs based on the construction laid out in this blog post that I linked to essentially create these bilinear maps to create your VRFs. Okay, so that's why I don't define E exactly, but you can imagine it's elliptic curve generation, or maybe something else. Okay, but what does it mean exactly to be bilinear, right? We haven't gone to that yet. Okay, so let's just say if you have E with 2 inputs, y to the x and then v to the power of y, you can essentially like factor out, if you will, or like push out these exponents outside the function itself, right? So you can have a more generic description of what it means to be bilinear than this, but this definition is sufficient for our construction of VRF, so we'll keep with that. We have 2 additional restrictions, one of which is has to be non-degenerate. So E of G and G is not equal to 1. We'll see why this is important later. And also it has to be computable. That is to say, there needs to be an efficient algorithm to compute E of U and V for any U, V, and G. Okay, and in this presentation, we'll define efficient algorithm as any polynomial time algorithm. So if you remember, polynomials are these things like x squared plus 3x plus whatever. This kind of family of functions are polynomial functions. And that's kind of what we'll use as our definition of efficient algorithm in this presentation. Okay. So now that I've introduced these new concepts to you, or maybe possibly old concepts, these concepts to you, now it's why do we care? Okay. And to motivate what we care, we need to learn some more new things, which are some cryptographic assumptions. Okay, one is called decisional Diffie-Hellman assumption, DDH assumption, which is to say, if you're given G, GA, and GB, distinguishing GAB from random is easy. Okay, remember, you're not given A and B, you're just giving the GA number itself. Next, we have the computational Diffie-Hellman assumption, which says, okay, given G, GA, GB, actually computing GAB seems to be hard. Okay, and then now we can note that these bilinear maps give us an algorithm for solving the DDH, right? The DDH in G, right? So how does it do that? We'll imagine that you have a G, GX, GY, and GXY as your DDH tuple. Then you can check that E, GXY is equal to, and because it is bilinear, you can essentially factor it out into just calculating E, GG, followed by the exponent of XY. And it's kind of how you would check your decisional Diffie-Hellman assumption. And then note, we needed the degenerate scenario because otherwise this entire thing over here would just be 1, and it would be very exciting, right? Everything would fall apart, which is why we had to exclude any degenerate case. And note, it also needs to be relatively fast because we need to perform this check in a relatively fast way, right? And so this is kind of why we had these other two assumptions or restrictions, if you will. Okay, so now we have some basic understanding of Diffie-Hellman assumptions. We're going to add two more slightly complicated but similar assumptions. Okay, one of them is called the Q Diffie-Hellman inversion assumption, which says there's no efficient algorithm that can compute G of 1 over X on the input G, GX, all the way up to G to the power of X to the Q. Okay, and the next one is the Q decisional bilinear Diffie-Hellman inversion assumption, right? Which is say no efficient algorithm can distinguish E, G, 1 to the X from random, even after seeing G, GX, all the way up to GXQ. And hopefully now that you've gone to this part here, you can see this is actually kind of what we wanted for our VRFs, right? We wanted an algorithm where we cannot distinguish it from random, right? Even after seeing possible other results, right? And so we will end up using this assumption over here to build our VRFs. And one additional notation, which is more of a computer science notation, is that if there's no t time algorithm A, where given q plus 1 elements, you get advantage greater than epsilon for solving the q db dhi, then we say that q tq epsilon db dhi assumption holds. So if you're not like a computer science or mathematician, just to briefly let you know, epsilon is usually used to represent an arbitrarily small number. And so in this scenario, we're saying if you don't get an advantage larger than epsilon, where epsilon is some small number. And what we mean by advantage is, imagine, for example, I run the VRF, and you try and predict what I'm going to output, right? If you can predict with a more than 50% accuracy, then we say your advantage is whatever your accuracy is minus 50%. So how much better you can perform than a random guess, right? And obviously we want to minimize that to as close to 0 as possible. So this is kind of where this comes from. Okay, so now that we have this covered, what is our actual VRF construction? Okay, well remember we had 3 parts to it, and we'll kind of go through one by one. So when we had our generate function, right? So you create a secret key S, where S is just some element of the group G. And then your public key will just be G to the power of S. Okay, when you run proof, which gives you the output of the function calculation, V of X is just this guy over here, okay, which is EGG to the power of 1 over X plus your secret key. Okay, and your proof of the correctness is just g to the power of 1 over x plus sk. Okay, so why do we pick this is what you might be wondering. Like, it seems really strange. Remember that the f of x is basically just based on this dB dhi, right? And then we pick the proof such the kind of the math works out for our verifiable, or sorry, our verify function, and we pick g in such a way that with our CDH, it turns out that you cannot easily figure out the value of the secret key, right? Or not, I shouldn't say the CDH, but like through all these Diffie-Hellman assumptions, right? You will not be able to easily figure out the secret key based off the value of the proof. So that's kind of how we pick these. And now that we have these two outputs for our verified function, we say, okay, our verified function checks if e gx times your public key along with the proof pi is equal to e to the gg, or no, just e of gg. Okay, and how we get there is just plain substitution, right? So remember, your private key is g to the s, so we input that right here, right? Remember from our definition of pi, we can replace it down here. Now that we have this, we take because e is a bilinear map, right? We take the x, the s, and we put it out here. We take the 1 over x plus sk, and we put over here. And then now we can cancel out this x plus s, and we're left with just e to the gg, right? And then lastly, we want to check that because we know g the input and we know pi, right? Because from at this point we're an external observer, right? We can check that in fact y is equal to this calculation right here. Okay, and this is our VRF construction. I just noticed there's a typo here. It should be VRF. Okay, and so with that, we want to add some extra definitions that we'll use later on in showing why this is a safe construction. And we say the size of G, the group, is a k-bit prime number. We're based off the security parameter k. Our input length is some function of k. Our output length is some function of k. And we have some security parameter or some security definition based on the value k. Okay, and then we say that a s prime epsilon prime VRF is one where no algorithm A, any algorithm A, can break the pseudorandomness in s prime k time with epsilon prime k advantage. Okay, so where exactly does this thing come in? Okay, so we're gonna have a theorem which is kind of based on the assumption that s2 to the power of ak epsilon dB dhi assumption holds for bilinear maps where g is the size of g is p. Okay, in the paper they kind of show why this is a safe assumption to make, but we're gonna exclude that from our video. So please just assume that this holds. And so you might be wondering why we take 2 to the power of ak, and I think it's because essentially if you have a binary number, 2 to the power of the size of the number is the number of possibilities, right? So remember, this is an input size in number of bits, and if you imagine you have like a 3-bit number, right? So you have like a 0, 0, 0, 1, 1, 1, so like a 3-bit number. There's 2 ways to pick the first digit, 2 ways to pick the second digit, 2 ways to pick the third digit. So the total number of possibilities for a 3-digit number is 2 to the power of 3, right? And so the total number of possibilities for an input size of ak is 2 to the power of ak. Okay, and then in the paper we essentially define an oracle, which says, okay, you give me an input x, and I will give you back the output from the VRF. Okay, And in the paper, we outlined that the calculation of a bilinear map, as I told you earlier, is polynomial in K, right? And then we say the oracle, with the calculations we have to do to compute the VRF itself, the entirety of the VRF, it takes 2 to the power of AK calculations. And so if, remember by the definition of the TQ epsilon dBdhi, this first S over here was time, right? The time of our algorithm. So if calling the oracle once to get a VRF output takes this much time, then the total number of times you could call the oracle, which is represented by S prime, is just the total time over here divided by the time it takes to call the oracle a single time. And remember, because calling our VRF will give you an advantage of epsilon, right? Calling the oracle to the AK times will end up giving you this advantage down here. And so this is kind of how we got this. Okay, and then so this is how we generate our S prime, epsilon prime VRF. Okay, brief discussion for extending the input size. So what happens if we only have small values of X? Okay, we can extend our domain, the size of our input, as long as we have a good hash function, right? By some definition of good, right? So for example, if you have a cryptographically secure hash function, you could take your input of size 5, maybe you have only inputs from 1 to 5, and you could hash it to a 256 bit number. So now your input size is 256 bits. And for example, if you want to shrink your input maybe back down to 100, you could take your 0 to 5, turn it into like some 0 to 256. And because of the property of a cryptographically secure hash function, you could essentially just chop off the first 100 bits. So now your input would be like a 100-bit number. So I shouldn't put 0, it should just be like a 256. Because the hash function also give you like 256 bits as a result. So you would take the 256-bit number and you would chop off the first 100 bits to get your 100-bit input. And so that's how you would extend the input size for your VRF. Okay, and so how efficient is this algorithm with respect to the properties we want from a VRF, right? And so for parameters deemed sufficient for your implementation of the bilinear map, which is given in the paper, we say that, okay, if you have 1,000 digits for your order of the group, then you can get a safe 160-bit VRF, okay? And then the proof and keys are 25 bytes length, which is the equivalent of 1,000 bits, okay? So how does this relate to blockchain, right? Well, if you think about blockchain and who creates the blocks, essentially like some sort of lottery system, right? In proof of work, you have a lottery based on who can burn the most cycles on some sort of computer, right? In proof of stake, you have some sort of lottery based on how much stake you hold in the system, right? So we want a lottery function, and the idea is, what if we could have a lottery function based on VRFs, right? So the first step would be, if imagine you have 100 people, you'll create an agreed upon random number, right? Some sort of source of randomness, okay? And then every block, every participant runs the VRF on some random number, right? And then after you run your VRF on some agreed upon input, I shouldn't say possibly like not agreed upon random number, but some agreed upon input, right? So you create agreed upon input, and every participant runs their VRF on an agreed upon input, and then everybody gets a result. And then we could say, for example, if your number is low enough, then you can make the block, right? So I run my VRF, I get 10, and I say, okay, if anybody gets a number smaller than 10, then they are the block creator. And so maybe I get 5 actually, and I say, okay guys, I got 5 from running my VRF, And not only did I get 5, I can prove to everybody I got 5, right? Because remember, it comes with a proof of correctness, right? So even though people don't trust me, they can run the proof and be convinced that I actually did, in fact, run the VRF and am the true block creator. Okay. There's kind of two problems with this that need to be addressed. Is one, you need to have some sort of Sybil resistance, right? And that's to say, what if I create 10 accounts, right? And I have 10 accounts and they each run the VRF, then I would have 10 times the chance of winning and becoming the block producer. So to combat that, you need to have something, for example, like weighing by stake. That is to say, instead of saying, okay, you get a number smaller than 10, you would say, okay, you need to get a number smaller than your stake on the system, right? That means the more coins you have on the blockchain, the larger your chances of being elected to become the block producer. Okay, and this is how one way you could fight the Sybil attack problem. One other problem that this brings up is that more than one person could be elected, right? So imagine I run my VRF and I get 5, which is smaller than my stake. Maybe I have 10 stake, and somebody else also runs their VRF and they also get a small enough number. And then now we have two block producers, and the system needs some way to resolve who's the true block producer. And so this is kind of one of the problems with the system. May also be an advantage, depends how you look at it. And as long as you use Nakamoto consensus, the system will eventually, kind of randomly, depending on the network topology, pick one person to be the true block producer. So this is kind of how these are useful in blockchains, and the one blockchain that actually wants to implement this is Cardano, and this is outlined in their Ouroboros Prowse paper. Alright, and that's it for this video. Hopefully now you have a good understanding of verifiable random functions, how they're generated, and their use cases in, for example, blockchains and lottery systems. Again, if you enjoyed this video, please follow me on YouTube, Twitter, and all that good stuff to see more videos in the future.